Well, welcome everyone, and welcome to AltaSea's Project Blue at Summer live chat with Dr. Burke Hales of Oregon State University. This is part of a series of live chats that AltaSea has been putting on. You can find this one when it's done and all the other recorded ones at altasea-project-blue at altasea-project-blue.org. I'll put the link in the chat in a minute, so you guys can find it easier. We'd first like to start this live chat off by thanking the Port of Los Angeles for supporting AltaSea and our community outreach live chats. They've been instrumental in everything we do, and we greatly appreciate them. And also, we'd like to take this time to welcome Oregon State University as a new partner. We're excited to join forces with such an esteemed university and grow our West Coast network for ocean innovation even further. We are so appreciative of the opportunities that will arise from this partnership, from summer internships to live chats like this to research collaboration. And really, there's no better way to kick off this partnership than with our first Oregon State guest, Dr. Burke Hales. Dr. Burke Hales is a professor of ocean ecology and biogeochemistry at Oregon State University. His research focuses on the ocean's carbon cycles at its boundaries, the seafloor, the air-sea interface, and the land-ocean margins. Hales is also an inventor. He invented something called the Burkelator, which I'm sure he'll explain better than I, but it's a system that has revolutionized shore-based ocean acidification monitoring. Anyway, I'm going to turn it over now to Dr. Hales. Thank you so much for joining us. We're excited to kick this partnership off, and with that, the floor is yours.
All right, well, thanks very much, and I'm excited to be part of the inaugural event here. I've prepared some slides that cover some work that we've done over the last decade or so, as well as some more recent work. And I'll just try to walk my way through these slides, and then we'll open it up to questions at the end of that. It should take me 25 or 30 minutes to walk through these. So please keep track of your questions as they arise. Okay, so what we want to talk about here is sort of the big picture all the way down to the smallest pictures and the things that we're thinking about. The big picture is really critically important, and it's important to understand the things that we know very well, but also it doesn't matter necessarily in a directly personal way if you don't think about what the local impacts are. And so that's what I'm going to try to do here. I also wanted to point out that this is work that has been done by a huge number of folks. My colleagues, George Waldbusser, our current and former students, some really stellar students who contributed to this work, Iria, Elizabeth, and Stephanie, but also with partnerships with the Pacific Coast Shellfish Growers Association through Andy Serbier, and our colleagues at UW and NOAA in Seattle, Dick Feely and Jan Newton. That's, of course, an abbreviated list, and there are many other folks that have contributed and shouldn't be forgotten. All right, so what I want to try to convey first here is that there are many, many things that we have near absolute certainty about. We know these things tremendously well. There are things that cannot be argued scientifically, observationally, factually. There are people who will try, and those people are wrong. And I want you to make sure that you understand that there's a foundation of very solid knowledge upon which all this works. And the first one is that we know that atmospheric carbon dioxide is higher now than it's been in at least the last million years, and it's rising faster than it's risen in any other natural event that we're able to observe. The upper plot here is the direct measurements of atmospheric CO2. The blue circles are those made in the atmosphere itself at the Mauna Loa Observatory site. The red circles were made of the air captured in ice core data, or in ice cores from West Antarctica, where the ice cores accumulate very rapidly, and we can get recent and highly resolved CO2 content. And the lower plot shows the carbon dioxide variation over the last 800,000 years. And what you see is that there's a lot of variation. It gets as low as 180 parts per million. It gets as high as maybe 280 parts per million, but never does it get higher than that until the last 250 years or so, and never does it rise as fast as it did. And if you were to take the plot from the upper figure and impose it on this figure, it would be that vertical red line there to the left. We also know extremely well, just from thermodynamics, this is chemistry 101, very well established relationships, that when the CO2 in the air, that's the PCO2 there on the right-hand side of that equation, when it rises, the CO2 in the water, that's the aqueous CO2 on the left-hand side, it goes up. Higher CO2 in the air means higher CO2 in the water. And it's just a simple thermodynamic relationship. And there's observations that prove this. Many observations. One example is to show, again, the Keeling curve in the red, and then measurements in the ocean at the Hawaiian Ocean Time Series Station in Hawaii near the Keeling curve. And the CO2 content in the water rises exactly at the rate that the atmospheric CO2 rises. We also know tremendously well where the carbon is coming from and where it's going. On large scales, we know exceedingly well how much fossil CO2 we've emitted into the atmosphere, and we know that because it's an economic concern. If anyone who's making money on things is keeping track of those things, and so we know exceptionally well how much fossil CO2 we've emitted in the burning of fossil fuel and the production of cement. We can measure the atmospheric accumulation really, really well. And over the last 20 years or so, we've pinned down the ocean accumulation numbers to within probably less than 10% uncertainty. Now, I want you to notice the year on the bottom of the slide. These are our numbers that were valid in 2008. It's now 12 years later. That ocean accumulation number is up to about 150. And I want to point out what these numbers are. A PG is a petagram. That's 10 to the 15th grams of carbon. A petagram is the same as a gigaton. So we're talking about a billion tons, 127, now 150 billion tons of carbon in the ocean from atmospheric CO2 rise. And just for scale, a ton is about the same mass as a Prius. And so if you're to think about that, we put the equivalent mass of carbon in the ocean as 150 billion Priuses. And that's all going in there. We've been able to measure that. We know exactly what it does. I promise I won't be chemical equation or reaction heavy in this presentation, but we also know with very, very high certainty what happens when carbon dioxide dissolves into water. It reacts with water to form an acid called carbonic acid, and carbonic acid quickly reacts with the other species in seawater to lower the pH and consume carbonate ions. The most important representation of this reaction is the one that I've shown here, which shows carbonate ion reacting directly with carbon dioxide to produce bicarbonate. And the best indicator that we have right now of these processes is measuring the CO2 levels. The next thing is that we know in proximal sense that what matters most now is the carbonate ion concentration. And the reason that we know that it matters most now is because organisms that make their shells out of calcium carbonate depend on that carbonate ion. This, if you can see my cursor, this is carbonate ion. Calcium is very, very abundant in the ocean. Carbonate ion is not so abundant. And so changes in the carbonate ion will change the stability of these minerals compared to their thermodynamic stability. There's a term that we call omega that tells us how we relate the abundance of carbonate ion and calcium ion to their thermodynamic stability. And when this omega number is greater than 1, you can have shell growth. And when it's less than 1, shells start to dissolve. And many, many organisms that we're familiar with in the ocean, from plankton to large coral structures, depend on calcium carbonate to build their shells, their skeletons, their reinforcements. So what is omega? It's a property of seawater, and it tells whether or not the seawater is a favorable place for making shells out of calcium carbonate. When omega is greater than 1, shell formation is favorable. When omega is less than 1, shell dissolution is favorable. And shell formers really like to have very high omega, greater than 1, 2, 3, much greater than 1. And the shell formers do worse when omega approaches 1, and even worse still when omega is less than 1. Ocean acidification, CO2 uptake from the atmosphere by the ocean, makes omega lower and makes things less favorable for shell formers. We've experimentally shown that organisms that make calcium carbonate shells don't like it when you take away carbonate. And these are experiments, old experiments now, for some mussels and some oysters. And as CO2 goes up, carbonate ion goes down, and the growth rate, the shell growth rate of these organisms go down as carbonate ion goes down. So carbon dioxide goes up, carbonate ion goes down. The seawater is less favorable for making shell. Shell growers grow their shells more slowly. We know, because we understand these effects, what will happen to the ocean on long time scales. This is an image for the year 2100, and it's for the calcium carbonate mineral aragonite, which is what corals are formed from. And this shows that in important areas, Hawaii, the Eastern Tropical Pacific, that we're going from favorable optimal levels up here in the red down to marginal to low levels in these areas. And so places that you think about going to vacation, to go snorkeling, to go scuba diving, to see the coral reefs, we're threatening those environments by lowering the omega, the stability, the favorability for forming these calcium carbonate minerals. So hopefully I've given you a sense of what we know and what we know with very high confidence. And the question is, why is there any contention? Why is there any uncertainty? And there are a number of these things that contribute to our uncertainty. The first one is what I call the pH problem. pH is a very, very challenging measurement to understand, but it's tremendously easy to observe. Anyone who goes out and buys a hot tub test kit can measure the pH, but you're not always certain exactly what that means. The measurements that we need to make need to be very precise, and the noisiness, the uncertainty in those measurements are large compared to that signal. pH is sensitive to temperature and salinity variations in ways that are more less well understood than we would like. And what we're finding, and I'll show some results here, that pH is really not itself what's driving the responses, at least in the near term. And so pH is therefore an indicator, and an imperfect one, of our actual conditions. And one of the things I wanted to point out is that if you were to just go to, Google and type in pH or a question about pH range, you'd see something like this color scale that I'm showing here in the upper right. And this is full of misinformation. What they're claiming is that anything greater than pH 7 is good for you, and anything less than pH 7 is bad for you. And there's a number of things that are directly counter to that. High pH, this is what Drano is. I don't think anyone should be going out and ingesting Drano because some Google reference said that pH 14 was healthy. Orange juice is down around here, pH 3 or 4, and orange juice is fine. It's not unhealthy because it's acidic. There are, however, some suggestions that these are harmful conditions. The next major factor in our challenge in explaining this is that carbonate chemistry is an inherently multivariate system. You cannot change one term in the carbonate system without having multiple other factors change. And so if you change the CO2 in the atmosphere, many things change in response. The pH changes, omega changes, bicarbonate ion changes, the dissolved CO2 changes. And so it's very hard to tell which factor is driving the responses that we see experimentally. It's also very difficult to do these experiments. The organisms themselves change the chemistry you're trying to measure. And this is from one of our student papers in 2014, where Dr. Rosie Gradovia did an experiment with cyanobacteria and started the experiments at high, medium, and low CO2. And by the time the experiments had progressed, the growth of the organisms themselves were altering the CO2 at tremendously high levels. And so it's very, very hard to mimic the appropriate conditions that are representative of what we're seeing. It's very easy to implement a perturbation. Get a happy sea urchin, put it in the bucket, you add some acid, and you get an unhappy sea urchin. But this is not representative of the scales of the perturbations or the time scales of the perturbations. There's a lot of natural variability. The ocean has its own carbon cycling that imposes variability and wide ranges in CO2 content, omega, pH variability. And these are all additive with the anthropogenic perturbation. The colored pictures that I'm showing in the upper panels are oxygen concentrations off the Oregon coast on the right in May and August of 2001, and on the left are the oxygen concentrations. On the right are CO2 levels, and it shows the tight coupling between the oxygen variability and the CO2 variability. And this is, of course, because CO2 is a product of metabolism. As metabolism progresses, oxygen is consumed, CO2 rises, and these levels of CO2 that we see in these waters through entirely natural processes reach up to several times greater than our current atmospheric values. It's also very hard to see a historical effect of what we would expect to see in terms of ocean acidification perturbation. This is a very long record of oyster recruitment in Willapa Bay, one of the largest oyster broodstock producing areas in the western US. And records were kept from starting in the middle 30s to present. And there's been a lot of variability in the oyster recruitment in this area. Some great years, some bad years, some very long runs of bad conditions, a rebound, again, a lot more variability. And we really didn't start to do careful ocean acidification monitoring in this environment until 2011. Organisms themselves have different sensitivity throughout their life cycles. I'll show you more examples, but these are larval oysters on the left, showing oysters in high omega shell favorability, favorable shell forming conditions, and on the left in low omega, and you can see the shells are smaller, they're misshapen, they're deformed in comparison to the good conditions. Adult oysters appear to be able to live through wide variations in these kinds of conditions without great sensitivity. So here's where our work starts to come in. We started working with the shellfish industry in 2009, following an event where all of the hatcheries on the West Coast started to fail to produce oyster seed stock. This was called the Pacific Seed Stock Crisis, and there was support generated for collaboration between academia, industry, and professional organizations, and it led to our identification of ocean acidification as a contributor and to subsequent mitigation strategies. And there's a wonderful paper by Alan Barton and others published in 2015 that explains this in great detail. This collaboration found that the larval success was determined by the omega in the water in which these organisms respond, with much less sensitivity to pH. And this was a paper that Alan Barton led in 2012. But how do we really know this? How do we really know that omega is the issue considering other factors? And are there effects that can be seen in the wild? As I said before, there's a lot of other variability going on, and this is some of our data from Willapa Bay, adjacent to the Whiskey Creek hatchery, where the shellfish seed stock crisis really was at ground zero. And you can see that pH varies, as does omega, as does the CO2 levels. And so in order to experimentally determine which factor is the most important, we had to come up with a method to decouple these covariances. And what we did is we found a way in the laboratory to manipulate the chemistry so that we could set one of the suspected parameters to be a constant and allow the others to vary. And we could do this with a set of 3 experiments that would allow us to isolate the effects of CO2 in the upper panel, pH in the middle panel, and omega in the lower panel. And what we saw was that there was effectively no functional relationship to CO2 over a wide range, from 200 microatmospheres, which is approximately the level of the Ice Age atmosphere, up to 3,000 microatmospheres, which is something that we don't expect to experience for a couple of 100 years, even at current CO2 emission rates. And what we saw was that the pH effect was minimal, but omega was a clear, strong, and highly predictive relationship. This was with 2 separate cohorts with many individuals and of 2 different species. And this really defined how clearly we could show that omega was the factor that was driving the response to ocean acidification as opposed to pH or CO2 for these organisms. And just because the visual effect of this is so clear, these are some scanning electron microscopy images that show larval shells in various conditions. And what we can see is that even in what we would consider to be relatively favorable pH or the same pH, as long as omega is high, we get symmetrical, smooth, large, healthy shells. But if omega is low, even at the same pH, the shells are rough, distorted, and deformed. So it's omega, and we think there's no question about this anymore. We have got a number of other publications and experiments that we've done that show that this is true for a number of different species, and it's really definitively the case for bivalves such as clams, mussels, oysters, who spawn into the water column with planktonic larvae. So what about trying to actually go out in the wild and looking at wild populations and wild conditions to try to determine if there's an effect? And I won't expect you to read all this fine print, but Willapa Bay is this important area for oyster production. It's a large estuary, the second largest on the US Pacific coast. It's got a large intertidal area variability, a number of different small rivers. But the important point about it is that it was one of the places where the non-native Japanese oyster, Chrysostria gigas, was able to get a foothold and gain productive and naturally spawning populations. It's been without a good natural oyster set for the last several years. And we studied a place that's known as the fattening line, which is the most favorable place for oyster production and retention in the bay. And what we found was that we could identify when there was an optimum in both temperature and omega conditions. And what we found was that the omega optimum was, number 1, more limiting than the thermal optimum, and number 2, phased later in the year. So in the early parts of the year, when the bay is warming up to favorable thermal conditions, the chemistry is not favorable. And so there's this asynchrony between the conditions, the chemical conditions for favorability, and the thermal conditions for favorability. So how do we tell if it's worse and how much worse? Well, we built a simple model, and the simple model had divided the bay into 3 parts: the one near the ocean at the bay mouth, the one up at the upper end of the bay where the rivers come in, and then the one at the mid bay, which is where the fattening line is. And we created a mathematical model for this and compared it to our measurements that we made using the Burke instrument. And what we found was we could reproduce the variability that we saw fairly well with this simple model. So the red line here is the model, the orange dots are the actual data. And what we can do is a pretty good job of reproducing the bay's warming, the bay's increase in salinity, and the bay's change in chemistry. We did this for 10,000 simulations to try to assess the contributions of the variability and the driving terms. And we did it for a circumstance for the modern ocean and a circumstance for what the ocean would look like absent the anthropogenic carbon. And what we find, and I want to focus in particular on the right-hand plot, what we find is that in the pre-industrial environment, the number of days where we had sufficient overlap between conditions that were warm enough and favorable enough for shell formation happened about 40% of the simulations. And this is consistent with what we see in the variability of good year, bad year variability in the oyster recruitment. When we add the anthropogenic carbon, that 40% goes down to under 15%. And so we've decreased the number of years with both favorable thermal and omega conditions by over a third as a result of adding anthropogenic carbon to this system. So what do we do? Well, if any of you saw the announcement to this on Twitter and saw my Twitter handle, you see the term seagrass won't save us. And the issue here is that seagrass is a rapid grower. It's a wonderful environment that's a nursery for many different species, but it doesn't stick around very long. Seagrass grows rapidly, but it also dies quickly. It turns over quickly. And so on time scales of seasons or years, we're not really taking very much carbon out of the water by growing seagrass. We take it out for short periods of time, and then we release it shortly after that. We're talking about trying to mitigate the effects of carbon dioxide that has been stored for tens of millions of years, and we can't do it with something that stores carbon for a few months. And one of the things that's important to look here, and this is from a paper from one of our students, Steve Bacella, and what you see is that I want to focus on the solid lines. The blue line is for when omega is less than 1.4, and that's a condition that we've identified as critical. And the blue lines, the blue solid line is the full model that has all of the biology, all of the metabolism of the seagrasses included in the model. And the red line is what the model would look like in the absence of the seagrass metabolic effect. And what you see is that the frequency with which we observe harmful conditions is actually higher in the seagrass inclusive case than in the seagrass exclusive case. Seagrasses are beneficial out in the future where they help to mitigate a baseline that's in general harmful, but under the current conditions, the metabolism of the seagrasses and the natural variability actually introduce exposure to unfavorable conditions. Seagrass is a wonderful environment. Seagrass meadows are incredibly important and should be restored, but it is not the answer to ocean acidification. So what do we need to do? We need to reduce CO2 emissions. And of course, that comes from our own CO2 emission reductions, thinking about the ways we use fossil fuels, the way we live. But the other thing that's just undeniable is that we have to think more about green energy, alternative methods for generating energy. And this is going to bring me to the project that I'm working on right now, which is called PackWave. And this is building a testing facility where the engineers, the industrial people who are building these devices that can capture energy from ocean waves can go and test their devices in a true open ocean, fully energetic system with an actual grid connection. So wave energy is an interesting tool because there's a lot of energy out there. Anyone who's gone to the beach can see the energy crashing on the shore. And we could potentially capture a significant part of our annual electricity usage. And the key point here is the fourth bullet. Ocean waves are relatively constant. We all think about solar, we all think about wind. Ocean waves don't set. When the sun goes down, the ocean waves are still producing energy. When the wind drops, the waves still keep pushing onto the shore. And so it's a different character of energy production from solar, from hydro, from wind. And so it's complementary. It adds a stable baseline to a green energy portfolio. So what is PacWave? Well, it's an open ocean wave energy test facility based at Oregon State University. We've got 2 sites, a research scale and an actual municipal power generation scale sites off of Newport. This main site that will be connected to the shore via cables buried below the seafloor is here, about 7 miles offshore, well over the horizon from the beach. We should be able to, at peak production, support up to 20 megawatts of power with a number of different wave energy production devices. And just to give you an idea of what concepts and what devices are in production, there are a number of companies internationally and nationally that are producing devices that are megawatt scale electricity production devices. And these are the types of devices we hope to be able to test at PacWave. A number of different technologies, turbines, rotating devices that produce electricity in a number of different ways. So this is where I'll wrap up and we can take some questions. And I just want to remember to fall back on the certainty of what we know. We know that we're producing fossil fuel CO2. We know it's being taken up by the ocean, and we know it's changing the chemistry and having an effect on ocean life. This shell mineral stability, omega, is the leading factor determining larval bivalve sensitivity, and it's happening now. This is not something that we're waiting around for the year 2100 to discuss. It's an issue that's happening right now. It appears that the natural variability of systems mean that there's always been conditions where things were not favorable. But the industrial carbon that we're adding to that system has reduced the favorable intervals by a factor of 3. Bioremediation is an excellent strategy for many things, but probably not for long-term carbon removal. What grows also decays. The long-term solutions to this require fossil CO2 reductions in emissions and development of technology and green power. And this is where we're starting to consider the potential for wave energy. So that's all I have, and I hope that there have been some questions that were generated, and I'll leave my presentation up in case there are questions that harken back to any of the slides that I've shown.
Awesome. Well, hey, thank you so much. It was awesome. We had a couple questions, and if you don't mind, I'd like to start with the PacWave wave energy stuff, because that's something that that once it seems almost like a no-brainer. And we've had machines like water mills for centuries, and kind of the from a layman's perspective, is that kind of what you're talking about? Is that the same concept?
Yeah, so there are, as I said earlier, there are a number of different ways of that folks have tried to do this, and I think it goes back even further than water wheels and that sort of thing. But essentially what we're talking about is converting kinetic energy to electrical energy, and if you can come up with a way to generate a rotation or an oscillation, you can convert that movement, that kinetic energy, into electrical energy. And the number of concepts that are being employed they're very familiar. The self-winding watch has got a mechanism that's very similar to some of the mechanisms that you see there. A yo-yo that lights itself up when you work it is generating electricity from that rotational kinetic energy. And so the trick is to figure out how to get oscillatory wave energy captured in a way that we can turn it into generated electricity.
Gotcha. So Ken wants to know what the projected cost of PacWave is and who's funding these projects.
So PacWave is primarily funded by the Department of Energy. And the projected cost to construct the facility with the subsea cables and the power conversion facilities and the grid interconnection, we're at a project cost of about 70 million right now. That 70 million is funded primarily by the Department of Energy, but there is a requirement for matching funds from the university. In addition to matching funds from non-university sources. And so we've got significant contributions from the state of Oregon. We've got a significant contribution from the Murdoch Foundation, significant contributions from the Oregon State University itself. And we also are continuing to fundraise because our obligation for matching funds is currently short by about $1 million.
So with those costs, how much electricity, this is kind of a bigger picture question, but you said there could be significant amount of our energy can be that can be replaced with these machines. What's your project? Could we see in 20, 30 years a whole coastline that's powered by the ocean?
There are so many layers to that question that I should probably have another session to have that discussion. So the suggestion that with a number of scaling and efficiency factors that potentially a third of the United States domestic electricity consumption could be supported by wave, that's out there. That's been suggested by the Department of Energy and a number of other sources. Right now, we're still in this testing phase. Wave energy is where wind energy was 25 or 30 years ago. And a big piece of wind's rapid rise is that it's logistically relatively easy to test a wind turbine. You just put up a tower. I mean, I understand it's very, very difficult to just put up a tower, and we're talking about millions and millions of dollars to build and deploy these turbines. But the challenges of deploying devices in the open ocean with cabled connections, with grid interconnections, with monitoring is huge. And so we're the first opportunity for folks to do that large scale testing.
That's awesome. So then we've had some questions about oyster hatcheries, to go back to that. So Nancy asks, do oyster hatcheries now monitor pH of incoming seawater at their facilities? And can they do anything at the facility scale to mitigate if pH is very low?
Nancy, pH doesn't matter. It's omega that matters. Gave a whole talk on this, Nancy. So the answer to that is that they're monitoring carbonate chemistry, and they're doing it in many of the hatcheries on the West Coast. And they're doing it using systems that measure comprehensive carbonate chemistry so that we know not only the pH, but also the CO2, also the alkalinity, also the omega. And the omega is really the critically important one for these hatcheries, because that's what matters to these larval oysters in the hatcheries. And yes, there are ways to mitigate those effects. It turns out that a number of the sort of aquarium chemistry solutions don't really work for this application. And what does work is a product that's called soda ash. It's sodium carbonate. You can get it at the farm, ranch and home farm feed stores. It's used in agricultural processes. And that's the chemical, that's the modification that you need to use to change the conditions to elevate omega to give you favorable larval productivity.
Gotcha. Nancy apologized for that, by the way. Robert asks, 50% of plankton have been killed off. The ocean produces 70% oxygen and sequesters CO2. Did climate change cause a reduction in plankton productivity, or is the reduction in productivity and carbon sequestration responsible for climate change?
Well, so Robert, you've opened up a lot of topics that we should discuss some more. The oxygen number is a misleading number, and again, you should have someone else discuss that. It's 70%. even within the folks in the community who are suggesting the oxygen is a or the ocean is a net producer of oxygen, the number has only ever been 50%. And it's actually misleading because the ocean is actually a net consumer of oxygen in its natural state. So, and it's always been that way. The continents produce more carbon and produce more organic carbon and produce more oxygen than the oceans do. And that's, as far as we know, always been the case. We don't think right now we can see a direct atmospheric CO2 effect on plankton biomass reductions. It's very hard to pin down. And so, no, we don't think the changes in CO2 chemistry that we're seeing in the bays is because of a reduction in ocean productivity. We think it's because of anthropogenic carbon. But yeah, great questions and things that are really important to discuss, because there are some things out there that have made it into the popular literature that are really confounding. They confuse our interpretation of things.
Yeah. So bringing it back to omega and pH. So Frankie says, as you stated, omega is the most important. But what do you think about companies that are only monitoring pH in aquaculture?
I think they're making a mistake. I think that was the case at Whiskey Creek, which is, again, the sort of ground zero for this problem. They were monitoring pH exclusively, and they could not adequately identify the conditions that were harmful with pH alone. And when they added our instruments that could actually quantify omega, Mark Wiegert said it was like driving in the dark and suddenly someone putting headlights on the car.
Yeah. So similar to that, we still hear people say that, planting seagrass is going to be a good solution for everyone. Why is that still the case? Why isn't is that notion still out there? If we have all the research that you just presented.
Yeah. I try to present analogies for why ideas take hold. And the best one I can think of is that, we all have bank accounts, we all have checking accounts, and, we all have, us academics have our TIAA-CREF accounts, and we all jump in and we look at the stock market go up and down. And the way that the seagrass carbon sequestration has been presented has been to only ever discuss about how fast seagrass grows. And so it would be like if you were monitoring your retirement account and you only considered good days in the stock market and you ignored all those bad days. And so that's what's happening. Seagrass grows and consumes carbon dioxide when the sun is out. And then most of that carbon dioxide that the seagrass has consumed in the day gets released at nighttime. And at least up here, in the sort of temperate to moderate latitudes, seagrass doesn't persist throughout the year. So we have seagrass in the summer, but then the seagrass dies off and decomposes in the wintertime. And so the seagrass proponents have had a tendency to talk about only the sunshine and not the dark. And there is a positive effect of seagrass, like I said, in many, many ways, ecologically, but it's not a long-term net carbon storage system.
Okay, kind of going off of that, because you said when it gets chillier out, it starts dying off. So what about the more warm year-round areas, like Baltaseed's based at the Port of Los Angeles? So so that's, their winters to us are still cold, but that is what it is.
Right.
But compared to everyone else, it's not too cold. It's like 60. So
and there are certainly places on the Gulf Coast, for example, where the seagrass meadows are year-round persistent. But the thing that you have to remember is that there's a limit to the area and the extent of seagrasses. And so the seagrasses can't grow through the surface of the ocean. And the change in the amount of carbon that's stored in seagrass from one year to the next is not very large. And so, if you were to think about your lawn at your house, that grass grows all the time, and in warm places it grows year round, but you don't really ever have more grass in your yard. And oh, sorry, my dog has joined the chat. Um, uh, but yeah, you don't have more grass in your lawn next year than you did this year. It's not like it just keeps accumulating, and you reach a static state where that amount of seagrass doesn't continue to accumulate. And what's happening is it's growing and it's decomposing, and you've reached a static carrying capacity, and it doesn't take out any more carbon.
Got it. So what you've been saying this whole time is true. It's not really a good viable solution.
Well, you don't store carbon for 60 million years with a seagrass meadow. And we're burning 60 million year old carbon, and that's the problem, is the time scale difference.
Wow, that's an amazing number. So William asks, do you know of any climate solution bills in Congress or state, local level that would support and improve innovations to renewable energy solutions like Packwave?
So we've been successful in working with Congress to increase funding to Packwave. The project was initially funded at a nominal $50 million level, and it was very, very quickly clear that that was insufficient, and we went to Congress, and the Oregon delegation in particular was really, really helpful in putting this through, and we got a significant increase of funding to bring us up to the level we're at now. There is, the Department of Energy has got what they call their EERE, and I forget the acronym, but the RE is renewable energy. And so DOE has got a large renewable energy component that has traditionally been dominated, historically been dominated by traditional hydropower. So dams really dominate the Department of Energy's renewable energy portfolio. Wind and solar have grown really dramatically, but water power is growing as well, although we're the runt of the litter, so to speak. And there are a number of ways that you can capture marine kinetic energy, tides, waves, even river energy capture that doesn't involve dams, what we call run of river energy production systems. Those are all funded under this office, separate from hydropower, solar, and wind.
Got it. So another question, Marissa asks, as a middle school science teacher, how can I communicate the importance of marine ecosystems and how the negative fluctuations we're seeing may affect my students' lives in local communities? In other words, why is this important?
So that's a great question, and we struggle with that a lot. You know, it's very easy for me to fall into chemical equations and mass balances and carbon cycle quantifications, and those don't really speak to the local folks. And you know, it's probably easier on the Oregon coast. I wouldn't say that the Oregon coast community is necessarily welcoming to the concept of climate change, but when they see the effects firsthand, when it starts to be a pocketbook issue, then that changes really dramatically. And for us, our work with the oyster farmers has been far more effective in messaging than anything we've done scientifically. And so you talk about the oystermen, the folks that we're dealing with, the hatchery operators, a number of them will say, we don't believe in climate change, but we believe in ocean acidification. And the reason they believe in ocean acidification is because it hurts their pocketbook. And we've shown them how it works, and we've shown them how to quantify it, and we've shown them how to mitigate for it. And suddenly it's a completely different situation. And then those become tremendously powerful messengers.
Gotcha. All right, Frankie has one more question regarding seagrass projects and algae. Because there are millions of dollars being allocated to those projects, what would be what can we do now to kind of move the conversation to the other direction? And This is a heavy question. Is
Yeah.
what are your solutions if you could
Thanks.
write the ocean health bill?
Oh boy. Well, so I think ocean health that's a broad question that's beyond carbon cycle, that's beyond ocean acidification, and uh, habitat mitigation, estuarine restoration. Those things are all tremendously beneficial for ocean health in general, and in a number of ways, if you make the environment in which organisms live a more protective, productive, rich environment, those organisms will be better able to respond to challenges like ocean acidification and warming. We can see that the reason that the larval bivalves, the shellfish, the mussels, the oysters, we know the reason that they struggle under low omega conditions, under acidified conditions, is because energetically, it's much harder for them to make their shell than it is in favorable conditions. And so if you think about, early child, excuse me, if you think about something like early childhood nutrition, right? We know that the kids who go to school with full stomachs do better, right? And they might go to a school that has got challenges, that's got institutional challenges, others, but if they get a good breakfast, they can respond to those challenges better than the ones that don't get a good breakfast, right? And so there are a number of reasons that even if we're not talking about, carbon sequestration, that making the environment within which these organisms live more favorable, more supportive, will pay back in terms of these ecosystems, in terms of these species.
Got it. Well, that wraps up all the questions in the chat. I don't see any more. But yeah, I mean, thank you so much. We all learned a lot. We learned it's not the pH levels, it's the omega, which I'll tell you, before this chat, I did not know that. So now I do. And thank you so much. Do you have any last words?
No, I don't. And I guess, with regard to nothing extensive, with regard to the pH, we certainly think there are conditions in which pH matters, but they're just further out. Omega is now, pH is a few decades from now.
Gotcha. Right on. Well, hey, thank you so much, Dr. Burke Hales. This has been great. And if anyone's looking for this to rewatch, to learn more, visit altac-project-blue.org. I put it in the chat earlier. I'll put it again right before we leave for convenience. Let me grab that. Thank you so much to Dr. Burke Hales. And we'll be having more of these. Our next one is in 2 Fridays from now, with Dr. Andrew Thurber, one of Dr. Burke's colleagues, and we're excited for this Oregon State partnership, and we just want to thank everyone for joining.
Thanks everybody for letting me kick this off.
Thank you. Have a good weekend, everyone.